One of the things I love about being in an Earth atmospheric and planetary science department is just how collaborative we are. The collaboration has been one of the best parts about being here.
We're Earth, atmosphere, and planetary science. We span all the scales from inside the Earth out to outer space. And so there's really a wide range of expertise here.
Purdue University is a great place to study space because we have so many fantastic faculty all over campus studying space from so many different perspectives. We have a fabulous engineering department that's working on getting us into space. We have folks in agriculture and biology working on establishing more effective habitats in space. How do we live in space? And we also have our friends over in physics and astronomy working on observing a more distant object to really leap into the future with Purdue space exploration. Studying Mars helps us better understand our own planet Earth because Mars is one of the best records we have of the early solar system and what planets like Earth might have looked like over 4 billion years ago. One of the great things about the Mars 2020 mission is that it generates all kinds of cool data. I work on the Mastcam-Z camera, which is a camera system that takes the beautiful landscape images that you see coming back from the rover. It also takes spectral data, multispectral data that we use to interrogate the composition of the landscape around us.
My research sits at the interface of earth science. I do a lot of work studying our own planet, and I also do work studying other materials from elsewhere in our solar system. I specialize in thermochronology, which is a subset of geochronology, where we're telling information not only about time, but about the temperatures that geologic materials have experienced as well. So when did this rock get heated up by an impact event? Sometimes we get to revisit questions, kind of outstanding problems in earth science that have existed for decades that other people haven't been able to answer. But because we develop new geochemical tools and new approaches, we can come at these questions with fresh eyes. But I'm really excited about the geochemical work that we're doing and the questions that it's going to be able to answer.
We work on severe storms, say thunderstorms or hurricanes, and then climate. There are different kinds of computer models that are out there, and we use a variety of them to really understand how hurricanes, how severe thunderstorms, extreme weather work, and that can help us to better predict them for the future. And so we do a lot of that work here at Purdue in the Rosen Center for Advanced Computing that works across campus, and so anybody can use those resources. And so they have a centralized computing cluster to study the questions that we're interested in. AI is really transforming our ability to predict weather across timescales, and it's something that's still rapidly evolving, but it's also still in its infancy. And so I think there's a lot of excitement about what abilities we're going to be able to unlock with AI-based models that we can use alongside our physics-based models and all of our data to make better predictions in the future.
There's this interaction between what we do as a human society and what the nature does. The seismology that is informing both us as a society and also the nature is through a phenomenon that we experience every day, which is vibrations. One of the coolest things that we are working on right now is that we are able to turn communication fibers that's already been deployed into vibration sensors. And how do we make full use of these terabytes of data? How do we store them? How do we process them in real time so that we can significantly reduce the data size, but keeping most of the information using our knowledge in signal processing and our knowledge of wave propagation, but also using artificial intelligence and machine learning.
Everyone knows about how critical drinking water is around the globe. I do a lot of field hydrogeology, and I go out and take measurements in the field, and I do a lot of isotope hydrology. I take students out and I teach them the basics. We go out and we do things like measuring stream flow, installing piezometers to measure groundwater levels, installing temperature probes and things like that to measure groundwater, surface water exchange. And then I teach them about how to do chemical analyses. If they're my grad students, for sure, they'll be doing geochemistry and isotopes at some point in their career. And we're starting to do more and more modeling in the lab as well, where we actually simulate in a numerical way what a groundwater system is doing.
In my research group, I have a number of graduate students, postdocs, and undergraduates who get to contribute to the research that we're doing. And they get to interact with both kind of really expensive and really unique instrumentation every day that is giving them skills And so they become very versatile Earth scientists.
Working on a Mars rover is perhaps one of the most awesome things you can do as an undergrad at Purdue University. It's a great chance to get really hands-on with planetary robotic exploration. The team requires all kinds of people to get involved, to analyzing the data every day, to helping plan the data. And the students here do help us with that, and they get a great chance to work with a really big team, make fantastic connections all over the world, which is a really, really valuable experience.
This is such a collaborative environment. I got the opportunity to work with students from all over the world in this lab, and I want Purdue to be able to keep attracting these people from all over the world so that, this future is for all of us.